Good afternoon. Welcome to the CERIAS Security Seminar at Purdue University. It's my great pleasure to introduce today's speaker, Professor Sam King. Sam is Assistant Professor of Computer Science from our neighboring institution, University of Illinois at Urbana-Champaign. He received his PhD in Computer Science from University of Michigan in 2006, I believe. Mm-hmm. And Sam's research interests are in security, experimental system design, and computer system in general. And today he'll talk about two topics in these areas.
Thanks, Inqui. So hello, my name is Sam King, and today I'll be talking about two main topics. The first one is we'll be discussing how to build more secure browsers and more secure operating systems. And in the second topic, we'll be discussing malicious hardware and how we can potentially defend against this emerging threat. So before I dive in and talk about technical topics, I wanted to just show some of the students who worked on these projects. And so the first one shown here is Shuo Tang, and he's also known as Maverick. So for any of you in your 30s and maybe saw a few movies, you understand the reference. But he's really the main guy behind a lot of the browser stuff I'll be talking about today. Now, a few of the other students are Hao Hui Mai. He's also known as the Enforcer. So if I get any questions I don't like, usually I send Hao Hui after you, but he's not here with me today. We also have Matt Hicks, who's also known as the Mailman. That's more of a reference to the way he plays basketball than anything technical, and he's the main student behind the hardware stuff I'll be talking about. So, as a general overview, first I'll discuss web browsers, and I'll spend about 2/3 of my time talking about web browsers, and then I'll spend the last 1/3 talking about defending against malicious hardware. And if you do have any questions along the way, please feel free to interrupt me. So, if you look at how the web has evolved over the last few years, it's transformed from a fairly basic system where you have the web browser, and the web browser is your main application. And the browser is used to view static HTML data. Well, recently, web pages have really transformed into web-based applications. And your browser has transformed into a platform for managing these web-based applications. So from a usability perspective, this has been great. We've had a number of different new applications like Facebook. You can conduct banking online, check your email, play games, watch TV, and all of the number of things that you're able to do with the web have been made possible by this evolution. But the downside is with this evolution has come complexity. And there's a lot of evidence that browsers and web systems are the number one target for attackers of computer systems. So if we look at attacks on web-based systems, they can occur at many different layers of your computer system. So up at the top layer, you have an attack on a web-based application, which could be something like a cross-site scripting attack. And cross-site scripting attacks are kind of like bee stings, right? So cross-site scripting and other web-based vulnerabilities are very common. In fact, they're the most common type of vulnerability on the planet. But for the most part, it might hurt a little bit, but it really doesn't do any damage. Maybe there are a few people who are allergic to bees, or maybe you have a cross-site scripting vulnerability on Facebook. This is the type of thing that can potentially be damaging. But, if you have a cross-site scripting vulnerability on ESPN.com, for example, it's effectively meaningless. So it's very common, but not quite so potent. Now, moving one layer down on the computer stack, we have vulnerabilities to the web browser. And these are kind of like snake bites. So snake bites are less common than bee stings, but they still happen. So for example, I've been bit by a snake before. And it tends to be the type of thing you remember. And they're much more damaging, where if an attacker is able to take over your browser, they can access all of your web data, and they can also have avenues into the computer system itself. Now, going one step further down the stack, if we look at vulnerabilities to operating systems and libraries, these are kind of like shark bites. And when you have a vulnerability in your operating system that somebody compromises, they've basically taken over your system. It tends to be the type, well, you don't actually remember a shark bite because you're pretty much not there anymore. And if you take a step back and look at this from a more conceptual layer, I would say that this is really a question of layers of your computer system. So the lower you go on your computer system, the more control you'll have. And the more control as an attacker, the more things you can do. So down at the lowest layers of your computer systems, there's really arbitrary things you can do. Now, all of these different types of attacks are important for us to study. And I've published papers in each of these different topics. But today, we're going to focus on the two lower layers, browser vulnerabilities and OS vulnerabilities. So if you look at how some browsers are built, they are what I consider a monolithic web browser. And so what this means is it takes all of your content and it jams it into the same protection domain. So shown here on this slide, we have what's Firefox running on top of Windows. And so, what's shown in red here are things that are part of your trusted computing base. And the trusted computing base means that if you get an attack in one of these parts of your software or your computer system, then the attacker can compromise the security of your system. So in Firefox, they'll have a bunch of if statements to try to keep web pages isolated. But for the most part, if somebody gets into Firefox, they're going to have complete control of everything that's going on. Now, because of this, researchers, including myself, have proposed newer browser architectures where you can use something called a browser kernel that essentially decomposes the browser into a number of much smaller subsystems and provides a clean separation between the security logic of the browser and the implementation of the browser itself. One example of this that you may have heard of is Google Chrome web browser. It does something kind of similar to this. And it's great because you can, if your web app gets broken into, then you can still have pretty high assurance that it's going to be isolated. But one of the problems with these basic architectures is that they still have huge amounts of code that are part of their trusted computing base. So you'll note here on this figure, we have an entire operating system, 10 million lines of code, that's all fundamentally being trusted for the security of your system. Now, one might argue, well, we can use a microkernel like system to try to isolate components. And certainly, you can isolate traditional OS components using something like a microkernel, but it still doesn't get you far enough because all of these components are shared. So if you have an application and it needs to open a socket, it's going to go through your TCP/IP server. If your TCP/IP server gets broken into, any application that communicates with it is going to be susceptible to attack. So even though there's isolation, you still have to trust these components to do what they're supposed to do. So what we've done is we've built a new operating system and we focused on trying to make this one application, the web browser, more secure. And essentially what we've done is made browser abstractions first-class OS abstractions. And I'll talk about that a lot later today. But we've made browser abstractions first-class OS abstractions and lifted all these components up and have software for monitoring the interactions between them. And so with this in place, we can have very high assurance that even if these components get broken into, we can still browse the web safely. So as a general overview for the browser part of the talk, first I'll spend a little bit of time discussing the overall Iboss architecture. Then I'll describe our low-level mechanism for enforcing security policies called a security invariant. I'll talk about how we apply security invariants to a few of the subsystems within Iboss, and then I'll describe our evaluation before I conclude. So shown here is the overall Iboss architecture. Now down at the bottom you can see the Iboss kernel and the hardware, and these are both in red. And these are used to signify components that are part of our trusted computing base. Now up at the top we have something called a web page instance. And the web page instance is really one of our main principles here in our browser operating system. So it's kind of like a process. Now each time you click on a link or you type a new URL into your URL bar and you visit a new web page, you're going to create a new web page instance. Now, in order for this web page instance to do the things that browsers normally do, it communicates with a number of browser abstraction servers to handle things like user interface storage and network handling. And the key thing I'd like to point out here is that all the components running above your Iboss kernel, including your window manager and your device drivers, these are all outside of our trusted computing base. Now, the fundamental thing that makes Iboss different is that the Iboss kernel knows about browser level abstractions. So something like a tab, like an HTTP request, a cookie, these are all first-class abstractions in our browser operating system. And by doing this, we can make things much, much simpler. And so our goal is even if, for example, your network process or your network driver has been completely compromised, you should still be able to visit Facebook and do so without risking the confidentiality and integrity of your session. So the next concept I'm going to discuss is a security invariant. Now, this general idea of an invariant is something that's been used in many different areas of computer science and in fact beyond. So programming languages, people have their notion of invariants, operating systems have their notions of invariants, formal methods, and so on and so forth. And so I'll introduce yet another invariant, which is a security invariant. Now, to help motivate what a security invariant is, I've got a real-world example. So a real-world example of an invariant could be that you see fireworks on the 4th of July. Okay? So if you see fireworks, you know that everything's okay. Now, it doesn't matter how those fireworks end up getting in the sky. It could be a kid with a match lighting off fireworks, or it could be a sophisticated computer-controlled, coordinated fireworks show, or maybe as shown here on this figure, this Google Doodle, you have a Rube Goldberg machine where you have to kick a football and a bird eventually leads to an iron lighting the firework. Independent of how the firework ends up getting in the sky, as long as you see fireworks up in the sky on the 4th of July, you know that everything's okay. So the key thing we want to do is we want to apply this basic principle to our browser operating system. So what this means is we want to be able to check key security properties of each of the different components of our system without having to understand exactly how they're implemented. Now, the key challenge in being able to do this and being able to apply security invariants to our system is figuring out how to decompose and architect our system in a way that we expose the right abstractions for us to be able to enforce high-level browser security policies using security invariants. Now, before I talk too much more about the security invariants, I did want to introduce the Iboss label. And this is the key entity by which all of our security decisions are predicated. And for Iboss labels, they're made up of the origin of an HTTP request. And this is consistent with current browser security policies. So what this means is it's the protocol domain port tuple of a URL makes up a label. And one of the interesting things we do with Iboss is we infer labels automatically instead of having applications specify labels like you would in an information flow system. But in the interest of time, I'm not going to talk about the details of this inference. So shown here on this slide is two web page instances for two separate web pages that a user might want to visit. One is for google.com and the other one is for cs.uiuc.edu. Now what Iboss is going to do is it's going to create two different web page instances to handle these web requests. And what it will do is it will parse out the label from the request, and the kernel will automatically apply this label to each of these web page instances. So Google will get a Google-based label, and then UIUC will get a UIUC-based one. And then once these labels are in place, all of our security decisions are predicated off of that. Now, once the web page starts loading, it's going to make a number of network requests. Now, the Google web page is going to visit google.com to get the main HTML. Maybe it grabs a few ads. Likewise, with UIUC is going to go to cs.uiuc to also grab the main HTML. And so one of the things that we did with Iboss is we wanted to separate out the handling of network from the web page instance itself. So if you'll notice on the right, you can see that some of these network processes are given different labels depending upon where the request was made to. And so what this does is it provides a clean separation for us to apply different policies to network processes than we would to web page instances. And it does it in a way so that these entities are all visible to our kernel. So it's our underlying kernel that's making these basic security decisions. Now, for network requests in general, there's some details that I've omitted here. There are things we do on the return path. There are things we do to make sure that ads.com is separate for UIUC and Google. But in the interest of time, I'm not going to discuss any of that. So, one of the key things that's important about our overall architecture is being able to deal with device drivers. Now, device drivers are tricky because they're fundamentally shared by all of your applications. Now remember, we want somebody to be able to break into your network interface driver and still be able to send network packets without risking the confidentiality and integrity of your data. And the key mechanism we use to supply this type of functionality is we have a split driver architecture where we provide a separation between the device logic and the programming of the underlying device and the management of DMA buffers. So to give you a more concrete example about what this means, I've got an example shown here for sending an Ethernet, a series of Ethernet frames across the network. So shown here on this slide, we have a network process that's been labeled with ads.com and should make requests to ads.com. Then we've got a NIC driver on the right, which handles the programming of the underlying driver, and then the Iboss kernel, which manages DMA buffers. So what will happen is if somebody makes a network request to ads.com, the network process will take this, it will form an HTTP request and then form TCP frames and form IP frames until it finally gets to a set of Ethernet frames that it then sends down to the Iboss kernel. Now what the Iboss kernel will do is it will inspect these Ethernet frames and TCP and IP frames, and it will check to make sure that the TCP port for these particular frames are equal to ads.com and that the IP address is also equal to ads.com. So by doing this, we know that these low-level network requests are headed to the correct place given how the network process has been labeled. Now once the Iboss kernel vets the data, it will copy it into a DMA buffer. And once it's copied it into a DMA buffer, it notifies the NIC driver about the address of the DMA buffer. Now, one important distinction here is that the NIC driver doesn't actually have a pointer to the DMA buffer. Now, it knows the physical address where the DMA buffer starts, and it can program the underlying device with this physical address, but it never actually has a pointer to the DMA buffer. So this is why, even if your NIC driver is completely compromised, we know that it can't modify any of your DMA data. So the final check we have is after the NIC driver has received this notification about a new transmit buffer, it will program the underlying card to send this out across the wire. So the final check we have is a very small device-specific state machine that runs inside our Iboss kernel that validates, in fact, the sequence of in and out instructions is setting a transmit buffer, and it is setting it to a pre-validated DMA buffer. So taking a step back, what I've shown here are a number of small checks that we provide along this path that give us the high-level assurance to know that if we have a network process and it's able to send data out across the network, it's consistent with our browser security policy. And so this is how we use security invariants for device drivers. Now, another aspect of this project that we spent time looking at was the window management side of it. And this is a part that's often ignored by many researchers, but we thought for having a practical application like a web browser, dealing with window management and video drivers was something that was hugely important. So shown here on this slide, we have the basic flow for what's called a frame buffer video driver. And the way a frame buffer video driver works is that you have a big chunk of memory and you write pixel values into this big chunk of memory. The video card then reads these pixel values in and displays the pixel values on your monitor. This is a pretty basic way to set up a video driver. But the key advantage it gives us with Iboss is that it enables us to use page level protections to provide some display isolation for what gets displayed on the screen itself. So shown here is a screenshot of Iboss. So just as a quick aside, when Shuo gives this talk, he actually gives it live on Iboss. So that's pretty cool. I've already done my Purdue demo. So last time I was here and gave a talk, I installed a virtual machine-based rootkit on my laptop and finished up the talk. So I'm demoed out here at Purdue. So you guys just get the bitmap shot here from what I grabbed from Shuo. But shown here is a screenshot from Iboss. Now first I'd like to direct your attention to the top of the screen. And there, it's kind of hard to see, but we've reserved a very small portion of the screen specifically for the kernel. So what we can do is with the kernel, we can display the URL of the current web page that's being displayed. So it gives at least a very small visual cue as to what's going on. Now, one level down from this, you can see the buttons and bookmarks that are part of global state for the browser, which is commonly referred to as the browser Chrome. And this also is given the basic information that you need to navigate through your browser. And then finally, down at the bottom, we have the content that's being displayed by a web page instance itself. Now, the key thing that's important about this particular slide is that each of these components are isolated from each other. All right? So if you have an attacker and they break in to your web page instance, they can't overwrite your Chrome and they can't overwrite into the kernel area. And that's because we're using page level protections and security invariants to make sure that this doesn't happen. Likewise, if somebody breaks into our window manager or into our Chrome manager, then they can't overwrite the content that's in the web page. And then finally, we've got a little bit of redundant information up at the top that's from the kernel, and we're trusting. So because we're using page protections, we're able to isolate these different components from each other, even if they're completely compromised by an attacker. Now, in addition to isolating portions of the screen, we also use page protections to isolate different tabs from each other. So as I mentioned before, a tab is a fundamental abstraction in our system. So we know the current tab, and we can make sure that only the current tab has access to the screen, and and only the current tab can receive mouse and keyboard events. And we can do this through the series of checks inside our kernel. Now, in addition to the basic UI, we do have some support for basic storage architecture, but I'm not going to talk about it in too much detail. Basically, what our storage system does is it stores key value data pairs for doing things like cookies and HTML5 local storage. Now, the thing that's a little bit interesting about it is that the Iboss kernel will encrypt any of this data before it stores it. So that's why we don't have any security invariants for our storage subsystem. We just use encryption and we don't worry about it. Now, it's true that we could potentially get some data deleted, but at the very least, we'll have the confidentiality and integrity of that data will be assured. But I won't talk too much about that. Now, in our current implementation, we use L4 Pistachio as a starting point, and we use the MMU abstractions and message passing interfaces provided by that, and we build up our overall Iboss kernel using this as a starting point. We have E1000 Ethernet drivers, mouse and keyboard drivers, and a frame buffer video driver that uses Qt software rastering system, which turns out is actually quite efficient. We also use WebKit for parsing and rendering HTML and handling JavaScript, and we use the Qt port of WebKit. Now, something I didn't talk about at all today was that we also have support for traditional applications. And I think the key idea here is that you can build traditional applications on top of the abstractions provided for the browser. So basically, you can build up general purpose OS abstractions on top of browser abstractions. Now, we have only a few simple traditional applications so far. Mainly, we have the C runtime and Qt libraries ported, so anything that uses those should work in our system. But we do have a PDF viewer as well. And we ran experiments on the Intel Core Quad CPU running at 2.33 gigahertz and 4 gigabytes of RAM. So to evaluate our browser, if you remember, our high-level goal is to design a new operating system to make web browsers more secure. So what we're assuming is that attackers can execute arbitrary instructions within each of the components of our system, and we're only going to worry about confidentiality and integrity. So attacks like denial of service are still very viable in Iboss. Now, I think we might be able to help with those, but it's not something we've looked at thus far. So we're focusing on confidentiality and integrity. So the first experiment that I wanted to show is counting the lines of code within the trusted computing base. Now, using lines of code is a hard metric for security is dubious at best. But at the very least, it gives you some rough ideas about the level of complexity that we're talking about. So shown here at the top of our TCB count, we have Firefox running on Linux. And using a very conservative count of lines of code, we came up with about 5.6 million lines of code inside your trusted computing base. So 5.6 million lines of code are what you're relying on every time you visit your bank. And this is just a huge amount of software. Now, Chrome OS is a project from Google that has some similar goals to ours. But one of the things that they do is they use a commodity Linux kernel as their underlying platform. And they come up with about 4.4 million lines of code in their trusted computing base. Now, Iboss, on the other hand, has 42,000 lines of code in the trusted computing base. So you can see we've got a few orders of magnitude difference here in the levels of complexity. So when you're over 1 million, it's really difficult for one single person to sit down and understand your code base. And things like formal methods are really, really debugging tools at best. Whereas when you're down around 42,000 lines of code, this is something that certainly one person can definitely understand, and things like formal methods come into play. Now, we haven't done that yet, but it's something that I think becomes a possibility when you've got this level of complexity versus the 4.4 million or 5.6 million. Now, the next thing we evaluated was we went through recent bug reports of vulnerabilities that happen in operating systems and libraries, and we tried to classify if Iboss would be susceptible to them. So of the 28 vulnerabilities that we looked at from 2010, and this runs through September, Iboss would have prevented 27 of those. Now, the interesting part is that there is one that Iboss would have not been able to handle. And so it turns out the E1000 driver, the driver we used, had a small bug in the way that it counted offsets for transmit buffers. And so essentially, this is kind of the same logic that we would have needed as part of our validation checks. So in general, if device drivers are compromised, this is something that Iboss handles well. But it does turn out that there is some device-specific code that runs in Iboss, and so there was one bug that I think we probably would have been susceptible to. Now, in addition, the main point of Iboss is to try to shore up these low-level libraries, but we also do improve browser security as well. So what we did is looked at 175 security vulnerabilities from the Google Chrome bug list, and we compared how well Google Chrome contained them versus how well Iboss contained or prevented them. And the reason we wanted to look at Chrome is because our opinion is for the commercial browsers that are out there, Chrome has the best architecture for security. So we wanted to see if our architecture for our browser could improve on that. So up at the top, we have a category that we call memory exploitation. So this basically means you've got a buffer overflow, and we're going to assume that attackers can execute arbitrary instructions. Now, as you can see, Chrome actually does pretty well here. Of the 82 bugs that were in this category, Chrome would have handled 71, about 86%. And this is kind of the vulnerability. This is not that surprising because this is the main reason why Chrome was designed. One of the key security benefits that they're providing is this type of isolation. However, there were still 11 of these vulnerabilities that were inside their browser kernel that they wouldn't have overcome. Now, Iboss, on the other hand, gets 76 of those, so it does slightly better. Now, the other thing that I wanted to point out is sandbox bypassing. So when you have a modern system, sandboxing is essentially a way of taking overly permissive or unused interfaces on your operating system and restricting them down. SE Linux is a great example of a sandboxing system. It turns out writing sandboxing policies and implementing sandboxing mechanisms is actually pretty difficult. And so there were 12 bugs that Chrome had revolved around those. And obviously any time that you can break out of the sandbox, the Chrome's not going to contain it. But in all of these particular cases, this is something that Iboss would have handled because it's just a fundamental part of our overall design. Now, in addition to assessing security, we also measured performance. And the way we measured performance is by measuring page load latency time. Now, a page load latency time is measured as the time it takes from when you click go until when the onload event fires inside your browser. Now, on the y-axis shown here, we have page load latency time shown in milliseconds. And on the x-axis, we have the 6 different websites that we tested where we looked at Google Maps, Bing, Craigslist, CS at Illinois, Wikipedia, and Facebook. Now we tested out 4 different browsers to see, to try to assess the overhead of Iboss. So we looked at Iboss, we looked at Iboss Linux, where we effectively took the Iboss browser and we ported it to Linux. We looked at Firefox running on Linux and Chrome running on Linux. And so, overall, the high-level picture, I don't want to spend too much time on this, but the high-level picture is, Iboss basically performs roughly as well as the other browsers. But the one result I wanted to point out here was CS at Illinois. So if you look here, Iboss is the slowest browser for CS Illinois. This is kind of embarrassing. All of these guys beat us on our own website. So I guarantee, if you guys see me give this talk again, next time we'll have the fastest one, at least for CS at Illinois. Like, I don't care if I have to change the website or hard code stuff into our browser. Like, we're not going to lose to Chrome on our own website. So, to conclude, but just a quick reminder, I've also got hardware stuff I'm talking about next. So to conclude the browser portion of the talk, the key thing that I showed here is if you make browser abstractions first-class OS abstractions, it gives you a much better starting point for building an operating system that can support browsers with high assurance. Now, what we've shown is that by doing this, we can reduce our trusted computing base by several orders of magnitude. It's a much, much simpler system with a much smaller layer of software that you have to trust. And if the components are broken into, we have enough checks to make sure that these components are contained from the rest of the system. And overall, even if you have components that are fully compromised on your system, you should still be able to visit trusted websites safely. So if there are any questions on the browser part of it, now would be the time before I move on to hardware. Yep.
So you mentioned your trusting computing base for Iboss is like 44,000 lines of code.
Yeah.
So does that include the device driver code?
No. So it includes a very small state machine for our device drivers, but most of the device driver logic is outside of it. And that's because for each of the device drivers we have an appropriate set of security invariants that we use to make sure that even if they're compromised, they're still doing roughly what they should be doing. Yep.
Is there a trade-off to have a small Iboss kernel as opposed to like these bigger kernels? Some
Yes.
kind of trade-off.
So there is a trade-off. So to be fair, we haven't completely evaluated this, but I mean the real trade-off here is for applications that aren't part of your browser, they're probably going to be slower than applications that are tuned for Linux. So for example, we've got these browser abstractions, and then for a traditional application like, I don't know, whatever your word processor that's running on your computer, you've got a layer to build up general OS abstractions on top of that, and then you've got your basic word processor. I'm assuming that's going to be slower. There are no security trade-offs. So you have the same security properties with your word processor that you have running on Windows 7 or Mac OS or any of these systems. But at the very least for Iboss you have higher security. But the trade-off, my guess, is probably going to be performance. We don't know if it's fundamental or not, but
Would it make sense to do all the stuff that you're doing with Iboss at the Linux kernel layer? So not just web browsers, but also other applications.
No, that wouldn't make sense. So I think the Linux kernel is, it's a great piece of software. Like I wrote my dissertation on it, but it's big, and there's a lot of code, and there are a lot of security vulnerabilities that happen in the Linux kernel. And so no, I don't think it makes sense at all. Okay, so now we're moving on to hardware. So just to refresh your memory, remember at the beginning of talk, I was up here and I waved my hands a little bit about these layers of attacks, and we had the shark bite was the baddest one of all of these. This was the lowest layer. So in the last part of the talk, we're going to discuss the killer whale of attacks. So this is the lowest layer, hardware. What happens if people can break into your hardware? It gets kind of crazy, but we've got some solutions that we think will hopefully improve. And so for those of you who can't really see it, we've got a very naive-looking shark that's about to get eaten by a very large killer whale. So whenever we build secure systems, we build these overall secure systems starting with a set of assumptions. Now, given these assumptions, we build up our overall secure system. Consequently, one very good way to break a secure system is to violate these assumptions. So for example, if I were to break a crypto system, I wouldn't attack the mathematical underpinnings of the cryptography. Instead, what I would do is look for the crypto keys in memory. Or maybe I would tweak the random number generator, make it a little bit less random. And by violating the assumptions upon which the crypto system was built, you can then break the security of the system. Now, what I would argue, one fairly fundamental assumption that most systems make is that the underlying hardware is correct. And so the question that we want to ask is what happens when you can no longer make this assumption? Now, one observation is that hardware is every bit as complex as software. Now, a lot of people think that software is more complex and it's not tested very well. But as it turns out, if you look at, for example, the Sun Spark Niagara 2 processor, this is a relatively simple processor, especially when compared to what Intel puts out. It has over 1 million lines of code in its VHDL design. So this is a pretty complex artifact, every bit as complex as an OS kernel. Now also, it is true that hardware uses testing and formal methods, but the Intel Core 2 Duo has had an average of 3 bugs per month in deployed hardware. And I would be willing to bet that that's probably more than the number of bugs people have found in the Windows kernel. So hardware is complex, and there's a real opportunity for hardware to become a vehicle for malice, just like software is today. So one of the first things that I'm going to talk about just very briefly is a project called the Illinois Malicious Processor Project, or the IMP. And what we showed is that it's possible to modify the design of a processor to implement very practical attacks. And really the key insight is that you can build a small piece of hardware that helps serve as a foothold for your overall system level attack. Now, as anyone who's taken an undergraduate hardware class knows, implementing hardware is difficult. In fact, according to Todd Austin, this is why they call it hardware. But as it turns out, implementing hardware-based attacks is actually quite easy. So the key here is that there are a number of pretty useful circuits running around something like a CPU. In fact, it's got a really efficient Turing machine sitting right there. So the key is to try to reuse the existing circuits that are already part of the design. So you can add a few little bits of logic here and there to your system, and you can implement very high-level, high-value attacks without adding huge amounts of code. Now, as I mentioned, I'm not going to talk about the details of the IMP project, but we did implement a number of malicious processors several years ago, and it served as a good learning experience for thinking about the defense, which is really the ultimate goal here. So the second part, the part which I'll focus the remainder of my talk on, is a project called BlueChip. And with BlueChip, what we want to do is detect potentially malicious circuits automatically and remove them from the design. So when we look at the design of a piece of hardware, at some point there's going to be a designer that will write a bunch of VHDL or Verilog code and design the overall hardware. And at some point, you could have another designer that either intentionally or unintentionally adds an attack to the underlying hardware, or to the design of the hardware. So the first part of our system is called UCI. And UCI is a design time algorithm that runs through the hardware design to try to find any circuits that might be part of an attack, which we call suspicious circuits. Now, once we've identified potentially suspicious circuits, comes the second part of the system, our runtime system, called BlueChip, which will essentially remove these circuits from the design itself and then add some runtime fix-up hardware and software so that you can do this safely and still usually make forward progress. So first, I'm going to discuss some of the details of our algorithm for detecting malicious hardware called UCI. So shown here on this figure, we have at the top an uncontaminated circuit, just a normal hardware design. And you can see there's a signal coming out of that called priv, which is the privilege bit in the CPU. Now there's some malicious logic that's attached to a mux that when it's asserted, it will pin the priv signal equal to 1, essentially giving the attacker supervisor mode privileges on the CPU. Now, one of the key insights of UCI is that the attacker is unlikely to trigger this attack during testing. So if you were running through a hardware design verification test and you were to trigger this attack, then you would see automatically, oh, my privilege bit is set equal to 1 when it shouldn't be. Something's going on. So we're going to assume that the attacker is going to avoid doing that. And it's actually pretty easy to do. But we want to try to use this against the attacker. So the way our algorithm works is it runs through all of the design verification tests and it tries to find sets of signals where the values are always equal. So what this means is that for this particular set of test cases, you can essentially create a wire between these two signals, okay? So you can put a wire between these two signals, and for these test cases, it will have identical behavior to what it would have had otherwise. And in essence, by doing this, we've then removed other parts from the design, or we've highlighted parts of the circuit. And in this particular example, we've highlighted all of the circuits that were part of the malicious aspect of the design. So the fundamental question here is, once we've identified these circuits that are potentially malicious or suspicious circuits, what do we do? So our idea is we remove them from the design. We just take them out of the source code. So we'll modify the source code and effectively remove it. Now, there becomes a dilemma here, where if we remove unused circuit, if we remove these circuits from the design and the circuits were part of an attack, everything's fine. We've just taken an attack out of the hardware. But the problem is, if the circuits are legitimate, now if they would have been activated during the running of the hardware, we could potentially run into problems. And that's where the second part of the system comes in, BlueChip. So what we do from the hardware perspective for BlueChip is we add some logic to the circuit itself to try to detect if this circuit would have ever been activated. So if the circuit that we effectively removed would have been activated, essentially what we do is flush the state of the hardware, and we throw an exception up to software. Now what the software will do is run as an emulation routine that handles this exception inside the operating system. And essentially what the software will do is it will then emulate the computation in software to essentially scoot by that piece of hardware that you removed. Now, I do apologize in advance for this obnoxious slide, but this is one point that everyone misses. So if you're checking your email and you've been paying attention at all for the second part, this is the one thing that I want you to get out of it. BlueChip does not emulate the underlying hardware, okay? So it doesn't emulate the low-level registers and logic gates that we've affected. Instead, what BlueChip does is it emulates the hardware at a much higher level of abstraction. So for a processor, what this means is we've modified some gates and muxes and these low-level hardware abstractions. But when we do emulation, we're doing instruction by instruction emulation, operating at a much, much higher level of abstraction. Furthermore, modern processors have enough redundancy in them that we can slightly perturb the computation in a way that we essentially route around the hardware we've removed. So for example, let's say that we remove the OR instruction from the instruction set and we get an exception. We can use NAND instructions to emulate the effects of an OR. So in effect, in software, we can emulate around that hardware that's been removed. Now, if you don't understand the details of it, that's okay, don't worry. But I will send you a pointer to our paper. So for the topics I discussed today, there are really 4 key papers that you could look at, and potentially more. You can go to my homepage, Sam King, if you're interested. The first one is the OP web browser. And this was really the first project in the browser line of work, where we were the first ones to take a look at decomposing the browser into a number of smaller subsystems. And it's a design that predates Google Chrome. This work was done with one of my former PhD students, Chris Greer. Now, IBOS was the work that I talked about for the most part in the beginning of the talk, and this is from OSDI 2010, and this was done with the students that I've already introduced. For hardware, there was a paper on how we built malicious hardware, and it showed up in LEET 08. And this was joint work done with Joe Tuchek, Anthony Causey, Chris Greer, Weihang Jiang, and Yan Zhou. And then finally, for the details of how we defend against this potential threat, you can see our BlueChip paper from Oakland 10, which was joint work done with Murph Finicum, another one of my students at UIUC, and a few of my colleagues, Milo Martin and Jonathan Smith from Penn. So to conclude, The basic theme of this talk is thinking about how to protect lower layers in our computer system. You know, there are many trade-offs where you have higher level applications, so it might be where more vulnerabilities are happening, but the more damaging attacks, and albeit the more rare attacks, are happening at the low layers. So we have two different ideas on how to protect the lower layers of our computer system. One is we want to modify the operating system and build a new one to try to make more secure web browsers. And the second one is BlueChip, where we try to identify and remove potentially malicious hardware automatically. So this is the actual conclusion and the end of the talk. Are there any further questions? Yeah.
So about the identifying malicious logic in hardware, so any of this kind of work, it would be one would want to know what's a false positive and false negative, right?
Yeah.
So how can you evaluate that?
So false negatives are notoriously difficult to evaluate, and we don't really have a good answer for that. You know, my hunch. So the way I look at UCI, the basic algorithm, is it's a first cut at this general type of thinking about security invariance in hardware, and you know, it may or may not end up standing the test of time. You know, is it sound? Is it going to detect all attacks? I don't know. False positives are actually pretty easy. So false positives, BlueChip handles those. So if you have circuits and they're not, and you identify it and it's not part of the attack, that's okay. You know, the BlueChip system will recover. And I've got lots and lots of performance results in the paper, but on average it adds like maybe 3% overhead. It doesn't occur very often.
So do you actually detect for example, the malicious attack that you did in your previous work?
Yeah, definitely. We definitely detect our own. So at least for attacks that are known in the public domain, we detect those without question. In fact, you know, those were the attacks that really helped us build up the intuition into the problem. So those we detect. You know, is there an attack out there that's going to get around UCI? I don't know. Maybe. Probably.
So the intuition is running through all your text specification. The malicious logic will not. What they are evaluating will not change. Is that right?
That's right. That's right. And so it's a very common pattern that we used when we were building malicious hardware. Whether it's the only pattern remains to be seen, but it's certainly a very common way to think about doing it. Yeah.
I don't have a button to push, so it's not.
I'll repeat the question.
So two things. So first, I guess as a comment, the other day we had here from
Sure.
OK Labs.
Yep.
And he was talking about the work that they had done for SCL board,
Mm-hmm.
verifying. And for that, for 8,000 lines of code, they have hundreds of thousands of lines of their.
Yeah, I know. And 20 years to do it. I
maybe
realize
the
this.
42,000 might be quite a bit of work. But based on that, my other question was.
Well, so I guess I have a comment to your comment. Instead of answering a question with a question. So I would say that we have already done some work formally verifying the API. So for some of our previous browser work, we modeled the overall API and model checked it, and we found bugs in our implementation. So, you know, I think that there are many, many different levels of formal verification. You know, are we going to formally verify Iboss kernel? No, probably not. We don't have 20 man years for 8,000 lines of code. However, I'm fairly confident there are many, many very significant things we can do, and our key approach is going to be to pick the parts of the system that we think are most complex and most security critical, and really focus on those. So I hear what you're saying, but I think we can make more progress than you might think is initially possible.
My other question was just going to be, since you're using L4, did you notice any significant overhead that occurs because of the IPC?
Sort of. So that's a tough question. So it was surprising. So, you know, one of the interesting things that I didn't really mention here is that the first title of the paper was Performance, Trust, and Protection. And we thought, you know, we'll use this microkernel approach, and we've got message passing and multi-core system. We're going to throttle people on performance. So we'll be the fastest browser out there. Turns out that wasn't the case. So we're still in the process of debugging the performance. But what we think is happening is not really the message passing is okay. Because if you look at our performance results in the paper, you can see the comparison between Iboss Linux and Iboss, where we're still using message passing in both, but Iboss Linux is a little bit faster than Iboss. What we think we were seeing is spin lock contention on the IPC channel. So we're not 100% sure what's going on yet, but we think that it's part of related to the SMP implementation that we were using.
Thank you, Stephen.